Hello everyone. Thanks for being here on day 4 of reInvent. I saw many of you were standing in the line, so I appreciate you being here. Let's keep this enthusiasm going. Let's keep the energy high. In today's session, we are going to talk about how you can use Amazon Bedrock and large language models. I'm just kidding. My name is Sid, and I'm joined here by Scott, and we are here to give your brains a little break from the large language model magic. And to be honest, I haven't quite figured out how to train an LLM to build global networks at scale with all the best practices and the scenarios which we'll be talking about today. So we'll do things a little old school. We'll talk about core networking concepts like network architects and engineers. Remember the good old days when managing your IT infrastructure just meant dealing with on-premises networks? And then came cloud and the promise of flexibility and scalability. And we entered into the era of hybrid networking. In fact, I've been doing hybrid networking sessions from the last 8 years. It's that important. But things are changing. With the rise of global economy and mobile-first users, your applications can no longer be deployed in one AWS region. So as you scale your applications into different AWS regions, your network connectivity has to evolve with it. Now, doing that at scale is difficult and hard to manage. In today's keynote, Werner Vogels brought up a very interesting concept of simplexity, building simple systems, simple architectures which can deal with complex requirements. And one such approach is to put AWS at the center of your network, powered by AWS Global Infrastructure and a software-defined service, which is AWS Cloud WAN, which acts as the brain of your network. Werner also said, complexity can never be created nor destroyed. It can only be transferred from one place to another. Fascinating concept. And we want you to take complexity out of your networks and hand it over to AWS so we can do the undifferentiated heavy lifting. You can connect your on-premises data centers to AWS using the brand new native Cloud WAN to Direct Connect integration. For your remote users, remote offices, you can use site-to-site VPN, client VPN, or go VPN free with AWS verified access. And Scott is going to touch on all of those topics today. Now, as you set up this hybrid connectivity, you have strict security and inspection requirements. That's where traffic inspection is key. And not just for hybrid connectivity, but also for application-to-application connectivity across regions, and in fact, even within the same region. We make it very simple with Cloud WAN service insertion. Now, Cloud WAN is the core of your network. At the edge, many of you have specialized application networking requirements, zero trust service-to-service communication, client-to-service communication, and with traffic management where you want to shift traffic on demand. And for those requirements, we have VPC Lattice and Private Link, and we have made enhancements to these services, which again Scott will touch upon in his part of the session. So let's start by talking about AWS Cloud WAN. Now, with a quick show of hands, how many of you are using Cloud WAN today? Okay, not a lot. So what I'll do is I'll do a quick recap of what AWS Cloud WAN is before jumping into some advanced concepts. You start by creating a core network, which is a high-level construct which contains all the AWS networking components which are managed by the service on your behalf. Everything you do in Cloud WAN is through a network policy. So we start by defining a network policy where we specify the AWS regions where we want to extend our core network into. Here, we are doing it in 3 regions. Now, when you execute this policy, Cloud WAN will create CNEs, core network edges, which are regional, highly available, highly resilient regional endpoints for all your connectivity. These CNEs are fully meshed with each other and exchange routes and traffic through BGP. Next, we create segments, which are first-class citizens when it comes to Cloud WAN. These are globally isolated routing boundaries. We define a network policy where we create 3 segments: production, development, hybrid. And in fact, for the hybrid segment, we are only extending it in 2 regions. Now, by default, you have end-to-end global reachability within a segment, but you can inverse that behavior by the isolate attachments flag and setting it to true. If you do that, all the networks that are attached and associated with the segment will not be able to talk to each other. Now, talking about attachments, you can connect your VPC to AWS Cloud WAN through VPC attachment. This is a fully managed connectivity, highly available, scalable. For your SD-WAN connectivity, you can connect it to Cloud WAN using GRE tunnels. Or we also recently announced tunnel-less connect, where now your SD-WAN appliances can exchange routes with Cloud WAN CNEs without need for any GRE tunnels. You can connect your transit gateway to AWS Cloud WAN. And even more powerfully, you can associate individual route tables with Cloud WAN segments and set up BGP dynamic routing between route tables in Transit Gateway and segments in AWS Cloud WAN. Finally, for hybrid connectivity, we have Direct Connect native attachment, which I'll spend a lot of time explaining how it works today. And then we also have IPsec site-to-site VPN. So these are the different native attachments which we support with AWS Cloud WAN. Now, once you have created these attachments, they are not associated with any segments yet. So for that, you need to create an attachment policy. Now, there are multiple ways of doing it, but my favorite is to use tags. So with this policy, Cloud WAN is going to look at the tag of your attachments and match the value of that tag with the name of the segment. And when it matches, it associates that attachment to a segment. Now, you can use this single policy to associate thousands of attachments to segments. But I know what you guys are thinking. What if somebody makes a mistake and tags an attachment in a wrong way, and you associate a development VPC to a production segment? Well, you have a flag require attachment acceptance, and you set it to true, then you add an additional human approval. And you can do that at a segment level. So you can say, for my production segment, any attachment association will require a human approval. But for my development and test, Cloud WAN can automatically make that association based on tags. Now that you have done the association, prod can talk to prod across regions, but you still cannot route traffic between segments. So prod cannot speak with dev, and hybrid cannot speak with your prod and dev environments. Now, if you have a requirement where you want to enable this traffic flow, you'll have to write another policy where you share your route, your segments. So here we are going to share the hybrid segment with the development and production segment. And once you do that, you can see now the hybrid workflow, traffic flows are enabled. All right, so that was a quick recap of how you go ahead and set up Cloud WAN. But setting up and building these global networks is just step one. It's very important to secure them and make them compliant. And that's where Cloud WAN service insertion comes in. With AWS Cloud WAN service insertion, we make it really simple to deploy centralized inspection architectures. You're no longer bogged down creating static routes. Now, all you need to do is write simple network policies. These policies tell AWS Cloud WAN how you want to inspect your traffic. Cloud WAN understands that and configures everything to make that happen. You end up creating compliant networks at scale. In order for service insertion to work, we introduced a new concept, network function group. It's like a Cloud WAN segment, which we saw previously, but it's purpose-built to attach to your firewall and security infrastructure. Now, everything is managed for you, but you do get full visibility into all of the routes behind the scenes. So in the next few slides, I'll walk you through some examples. For each example, I'll show you the network policy and what it's intended to do. I'll also show the behind-the-scenes Cloud WAN magic. you'll see the specific route it creates and how it automates everything. So here we have two AWS regions with two segments. We'll focus on the development segment to start with. And here, CNE1, region 1 regional dev route table, has 172.16 as the locally attached VPC, dev VPC, and 172.17 is one hop away via CNE2 in region 2. Similarly, in region 2, 172.17 is directly attached, and 172.16 is one hop away via CNE1. Fairly straightforward. Now we create a network function group, and we attach our inspection VPCs to the NFG. Next, we write a simple policy. Here, what we are trying to do is inspect egress traffic out of a segment, and in our case, the development segment. This is how the policy goes. Any traffic exiting segment development, send to NFG1. It cannot get any simpler than this. So, segment development action sent to via network function group 1. Now, when you do this, when you write this policy, what Cloud WAN is going to do is insert a default route into your route tables. And you can see the default route is now being populated. In region 1, the default route points to VPC inspection 1, which is this local inspection VPC. And region 2, the default route points to VPC inspect 2, which is its regional local inspection VPC. And it also populates network function group with the dev VPC routes. So when you do that and you initiate a packet flow from your dev VPC out to the internet, because we are talking about egress traffic here. The traffic goes to development segment, and it matches the default route. It's sent to the network firewall, which then sends it out to internet gateway. Internet gateway sends the packet back to the network firewall. The response gets inspected. Now it reaches network function group. Network function group has been populated with the dev VPC routes, so it knows how to send the traffic back. And now you're able to inspect all centralized traffic through globally. Now you might be thinking, I have to write this policy just for one default route. I can just go ahead and write a static route. Like, it doesn't solve any, it's not any less complicated. So let's talk through another scenario where you'll see the power of writing this policy. So you're expanding your global presence and you spin up the region, US East 2. But you don't have an inspection VPC in this region. So the development route table for region 2 has routes via CNE1 and CNE2 to reach the other development VPCs. Now we write the same policy. Any traffic exiting segment development sent to network function group 1. Now, because region 2 does not have a local inspection VPC, it can send the traffic to either inspection VPC 1 or inspection VPC 2, because those are equidistant for CNE2. So let's see what happens. So the traffic originates from a dev VPC, is destined to the internet, and it ends up going to US West 2. So the traffic from US East 2 ideally should be going to US East 1, because that's the lowest latency path. But in this case, it's going to US West 2. This happens because Cloud WAN is going to select one region at random. And that doesn't really meet what we are trying to do. So using the edge overrides policy, you can specify which region you want to use. So for US East 2, we will use edge location US East 1. And now deterministically, you can say, hey, from this region, I want you to use this exit path. Doing this previously was very difficult, and you had to create multiple route tables. But now with a single policy, this becomes very, very easy. So now you can see the traffic flows via US East 1. Now let's look at a different scenario. Here, we create the same policy for the production segment. So you can see the traffic now. When I previously was talking about examples, I was talking about egress traffic to the internet. But when I say a policy, any traffic exiting segment production, any traffic can not just mean internet traffic, can also mean other segment traffic. So what if a traffic is destined to a development segment? So the packet initiates, come to the the production segment, matches the default route. It is sent to the network firewall. Network firewall does the inspection, sends it back to the network function group. But you can see at the moment, the network function group is only populated with prod VPC routes. So it does not know how to send traffic to the dev VPC. So it drops the packet. Now let's add another policy to it. Here we'll write the send to policy for the development segment. And now the NFG gets populated with the dev VPC routes as well. So the same traffic from production to development. It comes to the production segment. From there, it's sent to network firewall. It gets sent to the network function group. And now the network function group has routes to dev VPC. So it's going to route the traffic. So what essentially you're doing is, and the reverse traffic as well. It takes the same reverse path, and you're able to route traffic between prod and dev. So when you use send to policy for two segments, you're not only enabling all egress traffic inspection, you're also enabling cross-segment traffic inspection. Now, if you intended to do that, that's great. If you did not want to do that, just be mindful that this happens, and you will need to configure your firewalls to drop that traffic. Now, if you intended to do that, that's great. But what happens when this is cross-region? So let's see how the packet flows. So now traffic is originating from a prod VPC in one region to dev VPC in another region. The traffic goes to production. Segment matches the default route, gets sent to the network firewall. It goes to the network function group. Now, network function group knows all the dev and prod VPC routes. So it's going to send the traffic to the dev VPC cross region. So the request gets inspected in VPC inspect 1. The return traffic comes to development segment, hits its default route. The response gets sent to the firewall in region 2, back to network function group, which basically routes it back to the prod VPC. So you saw what happened. The request went to one inspection firewall, and the response went to the other inspection firewall. So you basically end up with cross-region asymmetric inspection. Now, any stateful firewall will drop that traffic. So if you really wanted to inspect between segments, you should be writing a different kind of a policy. So let's talk about a policy to inspect traffic between segments. The policy goes like this. Prod segment, when sent to development, send via NFG. And in order to maintain symmetry, you have two options. You can say single hop, where you're saying deterministically, the request and response will be inspected only by one inspection VPC. And in dual hop, both the request and the response will be inspected by both the inspection VPCs. If you don't specify the mode, it's by default single hop. So let's look at the dual hop policy. Very straightforward. Production, when sent to development, send via using dual hop network function group 1. I love these policies. They are so intuitive. So let's see how this works. We are looking at CNE1 prod route table and CNE2 dev route table because we are routing between prod and dev. So when you execute this policy, Cloud WAN for the prod and dev segments adds an entry saying cross-segment routes point to in-region inspection VPC. So you can see now those routes get populated. Cross-segment routes, in-region inspection VPC. And for NFG, it says cross-region routes point to cross-region inspection VPC. I'm not showing that in the diagram here, but keep that logic in mind as we go through this packet flow. So the traffic originates in the prod VPC, goes to the production segment, that sends it to the local in-region inspection VPC. Now the traffic reaches NFG, and this is a cross-region route. So the NFG logic is send it to the cross-region inspection VPC. Right? So now it sends it to the inspection VPC in a remote region. That gets inspected and gets sent to the development VPC. Now the return traffic, I think I went too fast, but the return traffic basically takes the same route there. So you can see how this policy is able to do dual inspection. Now let's look at the single hop mode, which is a little more interesting. Now with the single hop, the same route tables, the Cloud WAN automation says, local region cross segment, the next hop is the local inspection VPC. So you can see that routes get populated. L stands for local region cross segment. And it says cross region cross segment routes. The next hop is a chosen inspection VPC. Right? So what's going to happen is Cloud WAN is going to choose one VPC at random and make it the chosen inspection VPC, which will be responsible for inspecting this cross region traffic. So in this scenario, our region 1 inspection VPC becomes the chosen inspection VPC, and those route gets populated. And NFG learns routes of all the dev and prod VPC, so nothing special with NFG going on here. So let's look at a packet flow. Here the traffic originates in a development VPC in region 2. It gets sent to the development segment, matches the routes, which is R because it's cross region, cross segment, and it's sent to the inspection VPC 1. So it does not send the traffic to its local inspection VPC, it sends to the chosen inspection VPC, and then it gets sent to the production. The return traffic follows the exact same path. Now, I know many of you are thinking, but Cloud WAN is going to choose the chosen inspection VPC at random. Like, do I not have control over it? You do. So with edge overrides feature, you can specify for an edge set which edge location to use. So here we are saying for US East 1 and US West 2, use the edge location US West 2. So now we are changing our chosen inspection VPC from region 1 to region 2. Our routes automatically get changed. And now you can see the traffic is flowing via the chosen inspection VPC. And our region 1 inspection VPC is all left alone with no packets to inspect. All right, so that was how you can use Cloud WAN service insertion and policies to deterministically do traffic inspection. Next, let's jump into our newest announcement, AWS Cloud WAN Direct Connect native attachment. Now with AWS Cloud WAN native Direct Connect attachment, hybrid connectivity architectures are greatly simplified. You no longer have to worry about creating transit gateways and using it in a path between your on-premises data centers and AWS. It also enables some specialized hybrid segment architectures, which we'll talk about today. So before you had this, well, see, even they like this new announcement. Everyone's excited. So before you had the Direct Connect attachment, you had to set up a layer of transit gateways. You set up your Direct Connect connections to your Direct Connect location. From there, you create transit VIPs to Direct Connect gateway. And then you set up connection to AWS Transit Gateway, which then gets associated with your CNEs. Now, the problem here was while you had dynamic route propagation from Direct Connect Gateway to Transit Gateway to Cloud WAN CNEs, the other way you had to set up static routes. And you had limits there, right? You had a quota of 200 prefixes which you could specify there. Also, Transit Gateway was an additional hop on the way, right? So now with the new announcement, that's gone. All you need to do is with a single API call, you can specify which edge locations, which CNEs you want Direct Connect Gateway to connect into. And then that connectivity is managed fully by AWS. And you get end-to-end BGP routing. So you have BGP route exchange from your on-premises router to Direct Connect Gateway, and then Direct Connect Gateway has BGP peering to the CNAs. Now, keep in mind that the basic fundamental laws of Cloud WAN still applies. So if you want to share these BGP routes with your production and development segments and the VPCs, then you will have to still write a policy to share route between hybrid and production and development. Okay, awesome. So let's see how the route exchange works when you set up this native attachment. We'll start by looking on-premises to AWS, so which is Direct Connect Gateway up to the CNE. So Direct Connect Gateway advertises all the transit WIF routes to all the CNEs. So here you have 3 on-premises data centers, and you are advertising 192.168.1.2 and .3 from your on-premises data centers. Direct Connect Gateway will learn all those routes and advertise 192.168.1.2.3 to all the CNEs. It does not do any automatic summarization. What you advertise is what it gets sends back up to Cloud WAN. The CNEs do talk to each other. As I said, they're fully meshed, so they will exchange those routes with each other. Now, from AWS to on-prem, CNEs will only advertise the local networks which it is attached to. So you can see here CNE1 only advertises 10.1.1, CNE2 advertises 10.2.1, and CNE3 advertises 10.3.1. It does not advertise remote region routes. So CNE1 is not going to tell Direct Connect Gateway that it has a path to US East 1 and EU West 1, even though technically it does. And I'll tell you why that's important. Now, static routes, if you have any static routes configured to non-Direct Connect attachments, those will also be advertised down. In my example here, I don't have that explicitly stated or showcased. So what routing behavior does this impose? The reason we do this is so that global routing for on-premises traffic is handled only by the Direct Connect data plane. Right. I'll show you with an example. So we have traffic originating from the on-premise data center. You can see on the corner there, and it is destined to US West 2. So the traffic is going from Dublin to US West 2. So it's crossing continental boundaries. The traffic is sent to Direct Connect Gateway via the nearest Direct Connect location, and from there, Direct Connect Gateway is going to route the traffic to the CNE and to the VPC in US West 2. The traffic will not be routed to the CNE in EU West 1, and the Cloud WAN data plane is not being used. Similarly, the return traffic is sent to CNE1. Now, CNE1 can either send the traffic down to Direct Connect Gateway, or it can send the traffic through its data plane to CNE3, which can then send it down. But CNE1 will send it down to Direct Connect Gateway. It will not use Cloud WAN data path. Now, why is this important? In today's keynote, Werner was talking about resiliency and having fault isolation boundaries, the cell-based architecture. And for hybrid traffic, we don't want you to have regional dependency. If you're sending traffic from US West 2 down to your on-premise data center, you should not have a dependency on US East 1 or EU West 1 as a region. These regions are supposed to be isolated fault isolation boundaries. Right? And that's the principle which we are applying here. That's why the routing works the way it is, and this is how you should be doing as well. Now let's take a different scenario where you're advertising a default route, or a summarized route from your on-premise data centers. So here, although your data centers have 192.168.1.2.3, you are advertising a summary route 192.168.0.0/16 through all your Direct Connect locations. It's a very common scenario, especially if you're using like a MPLS in between, or service providers, they typically advertise a default route up, a summarized route up. So now if the traffic is originating in US West 2 VPC and is destined to your on-premise data center in Dublin, the traffic reaches CNE, which automatically sends it to the Direct Connect Gateway. Now Direct Connect Gateway has 3 routes. It can send it to Seattle, to Northern Virginia, or Dublin, because it's getting the same prefix from all the 3 locations. So where does it send it to? So for that, if you look at our AWS documentation, you'll see every Direct Connect location has an associated region, and there's an affinity between a location and a region. So that affinity is important because the routing decision is always made to prefer that affinity. So we can say for US West Oregon, which is US West 2, Seattle Direct Connect location is associated. So it is affiliated or affinity to it. So the traffic will be sent via the Seattle location. Now what happens if there's a failure and the Seattle location is no longer available, or it wasn't there in the first place. In that case, let's see. The traffic comes back to Direct Connect Gateway, and then it gets load balanced. So the traffic originating in US West 2 is now getting load balanced to your Northern Virginia Direct Connect location as well as your Dublin Direct Connect location, right? So if the homed or the affinity-based DX location is not available, traffic will be load balanced. Now, sending traffic from US West 2 to a Dublin data center does not make sense. Not only is it crossing continental boundaries, it's higher latency. I think you would rather prefer it go through Northern Virginia. The good thing is you can set BGP communities, which overrides our local preferences. And this says all traffic on the Direct Connect Gateway should now prefer Northern Virginia location. Great. But we haven't solved the problem yet. Why? Because now the traffic which is originating in EU West 1 also will be sent to Northern Virginia. And we didn't want that. We wanted the EU traffic to go via Dublin, right? So what we really want to do is US West should prefer the nearest locations, and there's failure, it goes to Northern Virginia, and EU West 1 should prefer Dublin. So we want different routing configurations, and it is not possible with a single Direct Connect Gateway because Direct Connect Gateway is a single routing entity. So to solve this problem, we will create multiple Direct Connect Gateways. A Direct Connect Gateway has its own routing behavior. So by creating multiple Direct Connect Gateways, we can create unique routing behaviors and then connect and associate these Direct Connect Gateways to the CNEs where we want to impose this custom routing logic. So in my scenario here, I have one Direct Connect Gateway per region, and I'll associate and attach it to the CNE of that region. The CNEs will only advertise its regional routes to the Direct Connect Gateway. So for the global connectivity to work, I'll need to set up VIFs from my Direct Connect locations to all these Direct Connect gateways, but now have flexibility. So for the VIFs which I'm creating to the Direct Connect Gateway 3, which is associated with EU region, I'll use BGP communities to make Dublin data center or the Dublin Direct Connect location as my primary, Virginia as my secondary, and Seattle as my final option. Similarly, for my VIFs to DX Gateway 2, which is connected to US East 1, Northern Virginia becomes the primary, Seattle is the secondary, and Dublin is the tertiary. Right? And I'll repeat the same for DX Gateway routing behavior 1. So if you have number one, if you're advertising summary routes, only then this makes relevant. And if you have such advanced routing requirements, then this is the best way to do it. Now there's another great feature or functionality which has been enabled by this native integration, and that is end-to-end segmentation. So here we have production and development segments in the cloud, and we have production and development racks, switches on-prem. I'm assuming on-prem your development and production segments are in different isolated VLANs connected to a router which likely has isolated VRFs. So to extend this segmentation from on-prem to AWS, you'll create a Direct Connect Gateway dedicated for production. You'll set up a transit VIF with a dedicated VLAN from your on-premises production VRF to this Direct Connect Gateway. This Direct Connect Gateway only associates with the production segment. So here we don't have a hybrid segment. We are connecting the production Direct Connect Gateway directly to the production segment. You advertise your on-prem production routes, and from AWS you learn only the production VPC routes. You repeat the same, but now you create a development Direct Connect Gateway. A VRF, the dev VRF from your router to a VLAN, and then this Direct Connect Gateway associates with the development segment. You advertise development routes, and you learn development segment routes. So essentially what we have done is from your on-prem VLAN, we have extended that to your on-prem router VRF, which gets extended to transit VIF VLAN to a unique Direct Connect Gateway, which is associated to the Cloud WAN segment, and that connects to the route table. So you have now end-to-end segmentation. isolation of traffic from your on-prem into AWS. Now, what if you wanted to do those behavioral direct connects along with segmented direct connect? Well, that will lead you to create a lot of direct connect gateways. But keep in mind there's a quota. You can only create 4 transit VIFs per direct connect connection, and in this scenario, you've already hit that quota. So I don't want you to take this design and just go implement it. You have to be very mindful. Only if you have a certain requirement, if you want to do certain things, that's when you endeavor into some of these advanced scenarios and be mindful of some of the quotas here. Some of it is flexible, can be increased, some of it is hard limit, so you'll have to think about that carefully. So hopefully you see the value in getting rid of transit gateway and doing this native direct connect attachment. But how do you migrate to it if you already have it? So here we have a setup where we already have a direct connect gateway connected to the CNE via a transit gateway, the old way of doing things. In this scenario, the route received by the on-prem router will have a single ASN. And this is because direct connect gateway basically hides all the ASNs behind it and overwrites it with its own ASN. The route received by the core network edge from your on-prem router will have 3 ASNs. It'll have the ASN of direct connect gateway, it'll have the ASN of transit gateway, as well as your on-premises router, right? Now, when you start your migration, you'll create a separate direct connect gateway, and you'll create a new transit VIF onto it. You'll associate this direct connect gateway with your hybrid segment in Cloud WAN. Now, once you do this, you'll start receiving routes from direct connect gateway on the new VIF. But this route will have 2 ASNs. It'll have the ASN of the CNE as well as the direct connect gateway. So this will be a longer path. So if your routers are just following the rules of BGP, it will not send traffic via the new path which you just created. It'll continue to use your old path, so no disruptions. Right, so the old path is still preferred. Now, when you start advertising routes, right, the route which is received by the CNE over the new path only has 2 ASNs. It does not have the ASN of transit gateway. So CNE will start routing traffic, return traffic via the new path, right? So you need to be mindful. So don't advertise any routes yet. Start with test routes, right? Only advertise some test routes so that your return traffic only for those test routes is being sent by the new path, validate, test it, use local preferences on-prem to make sure that you're also preferring this path over the shorter path. And once you verify everything's working fine, take a maintenance window and then perform the migration. Right? Everything's working fine. All you need to do is shut down your VIF or remove the association from your transit gateway. The multiple ways to disrupt your old path. And as soon as you do that, the routing will be broken. Now, if you want to learn more about what we just talked about, there is a blog which we announced. Definitely recommend checking this one out. Now, for those of you who are not using Cloud WAN, I know what you're thinking. So, it's time to migrate away from transit gateway to Cloud WAN. Unfortunately, I will not be discussing migration strategy in today's session because I did it last year. I had a sessions very similar where I talked about how you connect transit gateways to AWS Cloud WAN and then you migrate your networks one by one. It's very simple, very straightforward. Definitely check it out. If you are building global networks on AWS, we recommend using AWS Cloud WAN. All right, next we'll talk about AWS VPN and some of those specialized network connectivity requirements. But to do that, I'll invite Scott over.
Thank you, Sid. So we've talked about direct connect integration with Cloud WAN. And I was really excited to see that launch because it simplified a lot of things for our customers. But what if you don't need the predictable performance and high throughput of direct connect? Or maybe you're in a location that getting direct connect to is just not feasible. Well, with AWS site-to-site VPN, you can connect to Cloud WAN over the internet using secure IPsec tunnels. In each of our tunnels, we connect to a CNE, right, in the local region. So we create our VPN connections in every region, And in every region, we set up our tunnels to our on-premises environment. For redundancy here, you can see that each of my on-premises environments are connected to multiple regions. So that way, if any individual region has an issue, you can fail over and connect to the other region. Inside of these VPN tunnels, we get BGP peering with our Cloud WAN segments, just like you would with Direct Connect, and we can exchange our routes. But what about our remote clients? Maybe developers that need to access our networks, work from home employees need to access our corporate networks, or other such use cases. With AWS Client VPN, we can set up a Client VPN into our VPC. We can enable multi-factor authentication. And then once we're in our VPC, we can connect out to other VPCs through Cloud WAN, through VPC peering, to on-premises through site-to-site VPN or Direct Connect, and out to the internet or other AWS services. But we live in a world where client VPN and connecting to a VPN isn't really required anymore. And for those use cases, you can use AWS Verified Access. Verified Access allows you to connect to your applications without a VPN. You can use both HTTP, HTTPS endpoints, as well as TCP endpoints now. And you can create per app policies, view your access records, and connect to your trust providers, your identity providers, your endpoint device management providers, and others. It gives us that fine-grained dynamic authorization, identification. Every request is authenticated. So if you create a change in your permissions, the very next request will either be approved or denied based on that change. You get improved observability, and you can use your existing security services, such as our partners. It eliminates the need to connect over a VPN and have your users have those complex things. And it gives you those ability for really fine-grained control that you don't get with a VPN, that layer 3 access control. It really brings it up to a layer 7 access control. We have third-party providers like Jamf, CrowdStrike, and JumpCloud that are all integrated with AWS Verified Access, and you can use today. But what about service-to-service integration in AWS? We've really moved from a world that has layer 3 access controls or layer 4 access controls based on IP or port or the protocol up to identity-based access control. Layer 7, application level networking. And with that, we have VPC Lattice. VPC Lattice allows us to have zero trust connectivity and use application control. So here you'll see we have Service Team A and Service Team B. And they need to connect to each other using HTTP or TCP. So to do this, we create our VPC Lattice service network, and we attach it to both VPCs. It's a fully managed data plane and a fully managed control plane. It allows us to do things like traffic control, as well as routing controls. It allows us to load balance, control identity-based access controls of what service can access what service. You can create network-based policies, right, across your entire service network in your organization. Or you can create service-based policies for individual services. And together you can combine these two policies to create really fine-grained access control. So let's look at what that granular access control looks like. We've got connectivity to our VPC Lattice service network. And we've got our billing service, our parking service, and our inventory service. We create our Lattice policy that says billing cannot communicate with inventory, but it can communicate with parking. And just like that, it works. That's it. That's all you have to worry about, right, is creating that policy. We don't have to worry about IP addressing and overlap because VPC Lattice takes that away from us. And we just connect to the service network using a DNS name, right, using a link local address. And we authorize and authenticate all of those requests through the service network. But what about a multi-region architecture and bringing Cloud WAN back into the picture? What does VPC Lattice look like then? So here you'll see we have VPC 1 and VPC 2 in our region 1, and then we have another VPC in our region 2. In region 1, we have our services connect directly through our service network. Super simple, super easy to set up. We then have VPC 1 that's connected to Cloud WAN and needs to connect to a service network in region 2. Well, this week we introduced service network endpoints powered by AWS Private Link. You create a private link endpoint in region 2 VPC, and you allow it to connect to your service network. You then send your request from region 1 through Cloud WAN to region 2 to that service network endpoint. It then enters your service network and travels just like it would if it was in a local service network. You can also do this from on-prem. Another thing that we've introduced this week, or last week actually, is in addition to the private link. With private link, we have a service in region 1 that sits behind a network load balancer. And we create our endpoint service, and we create an endpoint in VPC 1. But what about my service in region 2 that's behind a network load balancer? How do I get my instance in region 1 to connect to it? Well, we introduced cross-region private link, which allows you to create an interface endpoint in VPC 1 and region 1 that points to an endpoint service and a network load balancer in region 2, simplifying your cross-region connectivity. There's no need for Cloud WAN in this use case, right? We can really simplify our network. But the fact is that when you build scalable global connectivity, these things all have to fit together. It's not a one-size-fits-all. It's not everything's going to be in VPC Lattice, or everything's going to be in Cloud WAN, or everything's going to go across my direct connect. It's going to build a global network. And so when we look here at our global connectivity, we have region 1, region 2, and region 3. We have our Cloud WAN segment that's set up between those regions. We have our direct connect gateway to on-prem, natively configured into Cloud WAN. We have site-to-site VPN to our other sites that don't need direct connect or may not be feasible to get direct connect to. We have our remote users that have client VPN or verified access to connect into our VPC and then traverse through Cloud WAN out from there if need be. We have our service network with VPC Lattice to allow us to connect between services in a region. We have our service network in region 3 here, and we connect to the service network endpoint powered by Private Link from any of these locations. This is what a global network looks like on AWS when you really scale out. And you can use AWS to meet all of your networking needs, both from on-prem connectivity to AWS connectivity, cross-region, same region. We can inspect it all, and we can build out a global, scalable network using the power of Cloud WAN, VPC Lattice, verified access, and VPN, as well as Direct Connect. With that, I appreciate everyone attending today. If you have any questions for us, please join Sid and I right out back here or outside the conference room, or join us at our networking and content delivery booth in the showroom floor. Thank you.